Good morning, everybody. So I have the pleasure and honor to introduce the speakers of today's public outreach lectures. These are the public lectures of the Playing Colloidal Mikado workshop. My name is Dirk Aarts. I'm Professor of Chemistry at the University of Oxford. And before actually handing over to the speakers, I briefly want to explain a few things which are on the poster. And the first thing I want to explain is that these public lectures are part of the Playing Colloidal Mikado workshop series, which might be a little bit of an unusual name for a workshop, so I'll explain why we came up with this name. And secondly, I should highlight that this workshop is organized by the DieStruct network. So let me first explain the term DieStruct. So DieStruct stands for Directed Structure at the Mesoscale. Effectively, this is the name of our network.
Are you using a mic?
Sorry, I forgot the mic, yeah. I thought I could shout. Okay. Is that better?
Yeah.
So this DieStruct is part of is a European network, a Marie Sklodowska-Curie innovative training network, which is a highly inter and multidisciplinary consortium who are interested in understanding and exploiting the properties of colloidal liquid crystals. So liquid crystals we all know about. They can be found in our telephone screens, in our TV screens, and I will say a few more words about liquid crystals. But I will also, of course, explain the term colloidal, because that's a particular kind of liquid crystal. The network is spread out over Europe. We've got 9 partners, 5 in academia and 4 in industry. These are the different locations. The duration of this network is 4 years, so we just entered our 2nd year. And part of the network, actually the people forming the network, are 15 students who are all present here. And they will be trained to a PhD degree. And we receive funding from the European Union. So the name Playing Colloidal Mikado, so one of the things the network does is organize these conferences, and the name Playing Colloidal Mikado can be understood as follows. So our interest is in colloidal particles. And we all use colloidal particles in our everyday lives. For example, if you wake up and you brush your teeth with toothpaste, wash your hair with shampoo, you shouldn't mix that up, by the way. Eat some cheese, drink some milk, that's what we do in the Netherlands. Then actually we're eating and drinking and using colloidal particles. So if you use a powerful microscope and zoom in on the food or the personal health care products, you would find particles which are, roughly speaking, 1,000 times larger than molecules and 1,000 times smaller than grains of sand. So we're in the 1 micrometer range. As soon as you've got objects which are about a micrometer in size, it means you are dealing with colloidal particles. So colloids really indicates size. And just to illustrate that here, say a nucleus is super small, of course. An atom or a molecule is about 1 angstrom. And then if you go to the micrometer range, so surfactants are just on the small side, red blood cells are a little bit on the big side, but this is the range of colloidal particles. So polymers, DNA, proteins, they're all of the order of the colloidal range. These are grains of sand, so a millimeter. My children are roughly 1 meter in height. You can see them sitting over there. If you don't believe me, they're real, but they're here. So Stella and Tristan, they're playing with Jedi swords here. But I like to think that they're working out the overlap between 2 rods to do the virial derivation of the Onsager second coefficient. But okay, no. Anyhow, so etc. So this indicates the length scales, and here we are dealing with colloidal particles. Now, colloidal particles are clearly of practical interest because they can be found in foods, in shampoos, etc. They're also of fundamental interest, and since the days of Albert Einstein, we know that studying the properties of colloidal particles, we will learn fundamental aspects of nature. And the first speaker, Professor Roel Dullens, he will actually explain and show some of those links between colloidal particles and how we use them to understand how nature works. Now, this is explaining the term colloidal. then Mikado is a game we'll, I'm sure, know. It's actually a term not that much used in the English language. But Mikado is this famous pickup sticks, as it's called in American English. That's this game. These are actually the children of Pavlik, for those of you who know Pavlik, another member of the network. So we're a very family-friendly network. But this is a game, and the link is as follows. We can make our colloidal particles in the form of rods. So almost like Mikado sticks, and we can do that in the lab. So these are silica rods, roughly a micrometer in length again. And if you pack them closely together, they will spontaneously organize in what is called a liquid crystal. So this is a sketch of a liquid crystal, and this is actually a movie made with a confocal microscope of such a liquid crystal. And you can actually see the individual colloidal particles here, showing Brownian motion, showing diffusion by means of optical microscopy, confocal microscopy. And you can really learn about fundamental aspects of liquid crystals by studying these kind of movies. This movie, by the way, was made by Louis, who's a Dijkstrak fellow, and he's here in the audience. Right, so by studying these kind of systems optically, we can learn a lot about fundamental aspects of liquid crystals, also liquid crystals you use in your screens, your smartphones, and Professor David Dunmer will explain some links and some gives illustrations of liquid crystals, molecular liquid crystals, and colloidal liquid crystals in his in the second lecture this morning. Right. So. And then, sorry, so this is again a more fundamental link. Then we will end the public lectures by hands-on demonstrations of how to make fibers, because such colloidal particles can be used to make very strong fibers, and we've got colleagues from Teijin Aramid going to show how to make those kind of fibers. And Teijin Aramid is one of the companies who are also involved in the network. Right, so that's enough from me. So let me quickly hand over to Roel Dullens and Arran Curran. So Professor Roel Dullens is actually here. He's from the University of Oxford. Dr. Arran Curran is actually in Oxford. And we're going to do a live Skype connection where Arran shows things Roel is explaining. So that's going to be a bit adventurous, but Arran is online. Let me briefly explain that Roel did his PhD in the Netherlands. He got his PhD degree in 2005, cum laude, moved to Stuttgart for a postdoc, and in 2007 he started in Oxford, where he's now, together with me, running the experimental colloid group. Arran is a postdoc in our lab. He did his PhD at Heriot-Watt University, moved to Glasgow for a postdoc with Miles Paget, and for a couple of years already, he's now with us in Oxford. So without further ado, I'm going to hand over to Roel and Arran. Thank you. Okay.
Good. Thank you very much, Dirk. And it's very nice to be introduced by somebody who've been working with ever since I started working on colloids, which is about 15 years ago. So as Dirk said, my name is Roel Dullens, and I'm not really doing this talk on my own. I'm actually critically dependent on one of our postdocs in Oxford, Arran Curran. And the first live demonstration is, I'm going to show you his face. So we'll just have a look at whether this is going to work. Arran? Hello. We're live. So this is Arran. He's in Oxford in our lab. He had to get up. We've taken careful control of the time difference. So he's a bit. It's very early for him. But anyway, this is Arran. This is this is the optical setup. If you sit back a little bit, Arran, then we can see what you built. So we're going to do all the demonstration using this piece of kit, which took a good couple of 2.5 years to build. But this is where the sample sits, and this is another camera which we mounted onto a post, so we'll get a good view of the experiments that we are doing in Oxford. There you go. There you go. Don't have to do anything. I can just say, and then it happens. But this is our microscope, and I'll say a little bit more about this. So hopefully, at the end of this lecture, you have a bit of an idea what we do with colloidal particles and how we do it, i.e. microscopy and a bit of optical tweezing. And this maybe doesn't make any sense now, but it will be hopefully in an hour's time. Good, Arran, I'm going to go back to my talk. I'll see you in a minute. Right, so as Dirk said, all this work's been done in the Oxford Colloid group, which Dirk and I are sort of running in Oxford. And the title of my talk is Tweezing with a Twist. But tweezing really only refers to the last part of the talk. But what we are going to do is I'll talk to you a little bit about optical imaging and laser tweezing in colloidal systems. So Dirk has already introduced you to colloidal systems. I'm going to do the same few steps in the first few slides, but that doesn't really matter because it's good to see things twice. And then, yeah, we'll just slowly move on, and we'll see. We end up at optical tweezing at the end. Good. Now this is my outline. As I said, I'll just do another introduction to the micro world, in particular in colloidal particles, and I'll say a little bit more about what Dirk has already mentioned as to why we can use colloidal particles as superatoms, and then also talk a little bit about phase behavior, so why solids melt and how we can study that. Then the second part of the talk is about imaging, and I'm going to talk about two types of microscopy, just optical microscopy and confocal microscopy, and I'll finish off with the most spectacular part, which actually where we can, rather than just looking at them with a microscope, we can actually actively manipulate them using laser light. Good, so Dirk has already introduced you to this thing, so I knew this, but I put a different picture of his kids there. So, this is the definition from the IUPAC. And I just want to stress that again, right? So a colloidal particle or colloid really refers only to the size of an object, okay? So anything that's between, say, a nanometer and a few micrometers is a colloid, right? And it can be made of any material. It can be plastic, it can be fat, it could be a metal. It doesn't matter. It's only the size that is important in this case. And that's again shown on the scale bar here, so really subatomic particles, molecular atomic systems. And if you go to, say, a nanometer and a few micrometers, then you're in what we would call the colloidal domain. Yeah, and I'll show a few examples later on. So anything that has a typical size in this region here, which is, a micron, so your hair, or my hair, I don't know, is about 100 microns thick. Yeah? So it's typically 100 times thinner than your hair. That's more or less where we are working. And a good example, and I'll show that again. So this is a red blood cell, right? And that's a colloidal particle, just because its thickness and also to some extent its diameter sort of falls within this range. So that's a typical example of a colloidal particle that everybody knows, I hope. Now Dirk already showed the sound, and then Tristan and Stella, who are here, sitting front row. I also like to introduce you to my kids. So we have Anna, she's a little bit smaller than a meter. This is a little rabbit, Sami, and they're just enjoying their breakfast together. She's not quite a meter, but 2.5 kilos, quite. And then you go to a kilometer and 1,000 kilometers and bigger. But so what we're going to talk about really is this size range. Yeah, so that's what the colloidal domain is, as we like to call this. And just to give you a few examples, Dirk already gave half my talk. He said, I drank a glass of milk this morning. Maybe you did the same, and it's nice in England to show a Dutch can of, milk. But if you make a microscopic picture of milk, you put it under the microscope, and this is what you can see. And what's in there, for example, to mind the scale bar, a micron is right in the middle of the colloidal domain. Then you can see these flat globules here, which are typically, say a micron a little bit smaller. And that is what makes milk, well, white, but also makes milk a colloidal system. Okay? So, next time you drink milk or put it in your coffee, then think about, it's colloidal, and then drink it. Good. The next example is the red blood cell. You've seen this beautiful picture here, but here you see it with the scale bar. So this is 7 microns. I don't know why they picked 7, but this red blood cell is probably about 5 microns. But the thickness of these things is good tens, hundreds of nanometers, which again classifies this thing as a colloidal particle. So blood is another very important example of a colloidal dispersion, a colloidal liquid, a colloidal system, if you like. And yeah, I don't have to explain the importance of understanding blood. And in particular, also in our lab, we've done some experiments on blood where we actually took real blood and put it in a channel, in a small channel, in a little pipe, and we studied the flow behavior of these things under a microscope. Yeah? And this is for obvious reasons. This is very important to understand the flow behavior in channels, because that's what's happening in your body all the time. Yeah? But we can do that as well. Good. Another example, maybe slightly less obvious, is soil. Yeah? If you dig up some soil and you have some clay, you have these pictures here, this clay, or if it's dried up, it looks a bit like this. But the point is, if you put that under a microscope, then this is typically what you get. And again, the scale bar, micrometer, is right in the middle of the colloidal domain. And those small, well, I don't know if they're hexagonal, but they're plate-like colloidal particles in there, and that what makes clay also a colloidal system. Right? So it's really everywhere if you think about it. Even if you don't think about it and just listen, you can see it, right? It's everywhere. Paint, another one, which is really important. Yeah, all these colors things. And of course, you can also understand why it's so important to understand paint, i.e. why it's important to understand colloidal dispersion. Because if you put the paint onto the wall, you want to have a homogeneous layer. You want to get homogeneous coverage. You don't want to have any dripping. This has all to do with how colloidal suspensions flow, how they dry, and that's why you really want to study this. So I think, you know, companies like Oxford Nobel spend a good amount of money actually understanding colloidal suspensions just to get really good paint. Yeah, so the reason why you can see is colloidal. If you zoom in, take a microscope, you can really distinguish all that. There's no scale bar, but by now I hope you understand what the scale bar should be. Right, these typical structures are on the order of a few hundred nanometers a micron, and that's really, you know, what makes this thing colloidal as well. This is another, a little bit more exotic example. So bacteria, so the bacteria, these are magnetotactic bacteria. In this case, the bacterium itself is only a couple of microns, so we would classify as a colloid. But these particular bacteria, they have little nanoparticles in them. These are tens, maybe, yeah, tens of nanometers. So just towards the small end of the colloidal domain, but still classed as colloids. And you can see these little iron oxide particles, and that allows these bacteria to actually sense the Earth's magnetic field and orient themselves, which is an amazing piece of stuff from nature, but that's really a colloidal system as well. One that I'm very fond of is opals, so these gemstones, which are really very, very beautiful. And even if we make them in the lab, synthetic opals, they're also very, very beautiful. And they're very, very beautiful because they have all these beautiful colors. Right? If you illuminate, irradiate them with white light, you get all these different, all the colors of the rainbow are coming out. But the reason that is happening is because they're colloids. This is a colloidal system, and this was shown by Saunders, an Australian guy in the 60s. Because when you put these things under a microscope, what you see is that these gemstones are actually made of little silica particles. Again, the colloidal doesn't refer to the fact that it's silica, it refers to the fact that these are on the order of, say, 100, 200 nanometers. Yeah? Which puts them again in the colloidal domain. And that's the importance here. You can see there's all these regular arrays of these particles, and because you have these regular arrays, you get basically Bragg scattering, as you call it. You get basically the light is diffracted by the crystal, and then because of the interference, you get all these beautiful colors. And mind you, the reason that you can see it, because it all happens in the visible. Yeah, in the visible spectrum. So visible light, 400 nanometers, between 400 nanometers up to 700 nanometers. Yeah, that's exactly in the colloidal domain. And that's why colloidal structures actually really interact very, very nicely with visible light, and that's why you can see this thing. Yeah, that's not a coincidence. This is also the reason why we can use a microscope to see colloids, because usually if you use a microscope and you have light, then the structures that you can distinguish with a microscope shouldn't be smaller than the wavelength of the light that you're using. Yeah, so if you want to see things with visible light, you have to look at objects which are about the same wavelength, the same size as the wavelength of visible light, and this is exactly what's happening here. Good, we'll come back to the gemstones a little bit because they're very soft, right? You have to be pretty careful with these crystals because they scratch really easily, they break really easily, and this is going to be important for the actual last part of the talk. Good, so by now, I hope you have a little bit of an idea of what colloidal particles are, right? It's just the size that determines whether you're colloidal or not, and I've just given you a good few examples of where you can see and find them in nature. And this is, of course, also a reason for us to study them, because of all these applications, right? To do the application right, you really want to understand what you're doing. But there's another reason which is also important for Dirk and for, well, I guess a lot of people in the colloidal world, is that colloidal particles also behave like superatoms. And this is a little bit what Einstein told us. Now, you know, Einstein was in the news last week for something I don't really know about. But what is important for us is really this 1905 paper, right, where Einstein wrote this in German So I don't have the Dutch version here. But anyway, the point is that what he said is that a dissolved molecule is differentiated from a suspended body. And with the suspended body, I mean a colloidal particle in this case. Right? It's just sitting in water and it's just walking around, or in any solvent. Is only differentiated from a suspended body, a colloidal particle, solely by its dimension. And this is a key thing. So what he's saying here is that, to some extent, these colloidal particles do exactly the same thing as atomic and molecular materials, apart from the fact that it's bigger. Yeah? This is what Einstein said. And that's really important for us, as colloid scientists who want to understand why things freeze, for example, because we can look at colloids. Now, if a molecule is only differentiated from a colloid by its size, then you could ask another Nobel Prize winner, Richard Feynman, why would you bother with that? Yeah, because the same equations have the same solutions. Yeah, if the colloids do the same as the molecules, I might as well just study atoms and molecules. But then there's a third Nobel Prize winner here, Jean Perrin, who actually gave us a part of the answer already, because you can see them with a microscope, right? They're that big. You can use visible light, and you can use a simple optical microscope, and then we will do this in a minute, to actually see these things. Yeah? And this is much harder, of course, with something of the length scale of the size of an atom. You can't just take a simple microscope and just look at it. And you can certainly not see it move. Yeah? But with a colloid, that is very much possible. And that's very much what we do all the time in the lab. We look at them. What you see is what you get. That's very important. And this is what he saw. Again, mind the scale bar, 10 microns. So these these colloidal particles are about half a micron, nicely in the colloidal domain. And he did two very important experiments, confirming what Einstein already kind of thought about. And he got the Nobel Prize for this, 1926, for his matter on the discontinuous structure of matter. And this is going to be important. So the first experiment that he did is he looked at the behavior of these colloids when you put them in a gravitational field. So that's why gravity points downwards. That's why you have more colloidal particles at the bottom and less at the top, because gravity pulls them down, of course. Now, I don't want to go into too much detail, but what he managed to get from these experiments, he measured something called the Boltzmann's constant, which is related to Avogadro's number. And Avogadro's number tells you how many molecules you have in 1 mole. Yeah? And this, of course, implies that matter is made of molecules and atoms, which at the time was not even obvious. Yeah, so the fact that he could measure this Avogadro's number was one of the first and one of the early proofs of the fact that atoms existed. Yeah, and that's why he got sort of this Nobel Prize for the discontinuous structure of matter, the fact that the material is made of atoms. That's really important here. Matter is made of atoms. He did a second experiment, which was independent of this, but measured the same Avogadro's number, because he could look at these colloids in a microscope, but if you can look at them, a lot of images one after the other, you can also follow them. You can track them down, right? You can see where they are going. And this is the second experiment he did. So what I'm showing you here is a grid, and he made these pictures, and every dot corresponds to a position of a particle. Yeah? So this particle is moving around, and I'll show this in a minute. It's moving around, and every time you make an image, you make a dot, and that's how you can build up a trajectory of a particle. Yeah, if you made a trajectory of me kind of trying to stand still in the middle to actually make sure that the camera sees me, then I'm actually not, right? I'm just moving around all the time, and that's basically what this shows for a colloidal particle. And from this trajectories, he could measure something called the diffusion constant, and the diffusion constant is again related to Avogadro's number via the Boltzmann constant, and he had two independent measures, measured the same thing, and showed sort of the existence of atoms. So that's really important. So it's funny, right, if you think about this, that this atom was done using colloids, which are 1,000 times bigger. Good, we're going to go to Arran, because what I'd like to show you now is actually show this live, right? I'm just going to show you the Brownian motion, these particles moving around, and we'll actually do a live tracking experiment where we will build up such experiments. So let's see if we can find Arran again. Arran, are you there?
Hello?
Yep, good. So this is what you can see. So if you can you go to a very dilute region? Yeah, so if you just hold still there, so you can see these particles. These are colloids in our lab, live, happening now. And these are about 2 microns big, and you can just see them nicely walking around. Just this sort of random walk, which is what's called Brownian motion. And this is really important for Perrin. Arran, shall we do a live track now?
Yeah.
Good. So we're going to select a little bit, and with software, with computer software, we can, because of course we don't really want to do this with a pencil, right? We just want to do it with a computer. And down here, we can see we are actually keeping track of where this particle is moving. And we are, just ignore this bit, but you can see the random walk that Perrin had in his book just appearing. As long as you follow the colloid long enough, right, you can see this random walk happening. Yeah, so we're analyzing this image all the time. We're just determining the center of mass of this colloidal particle diffusing around. And this is the computer analysis live happening. And from this, as I said, you can get the diffusion constant, Boltzmann constant, Avogadro's number, etc. Exactly what Perrin did, but only about 100 years ago. But we're still using it all the time. So it's really a breakthrough experiment that he did. Good, so that's very nice. Great. Thanks, Arran. I'm going to go back to my presentation.
Okay.
See you later. So that was Perrin's experiment, Brownian motion, and live tracking going on. The next thing that is really important, because they do such similar things as atoms and molecules, is something called phase behavior. And what do I mean by phase behavior? I just mean states of matter. And everybody knows this morning was very cold, so there might have been some ice on your car. You had to get rid of it. And ice is, of course, a typical example of a solid. And if it gets a bit warmer, this stuff melts, and you get a liquid, and you have a glass of water. And then if you boil it in a kettle to get a cup of tea, you have gaseous water. And that's really what you would call phase behavior, right? So we're trying to understand how something goes from a solid, when is it a liquid, and how does it actually move into a gas, and how does this happen? And this is something which we can do with colloids as well, because they behave in a very similar way. Okay, now, while in a molecular system we go from a solid to a liquid to a gas, by increasing the temperature, we have a different control parameter in colloidal particles. Yeah, so before I do that, let me just give you an idea of how this looks. If I had a microscope and I could see the atoms, then this is a little bit how we think about a solid. So a solid has a lot of these atoms sitting very close to each other. In a solid, they nicely arranged on a lattice, so they have really the symmetry direction. This is a nice triangular or hexagonal lattice, if you like. And if you jump to the other side, then the gas is really diluted, just a very few atoms, and there's a lot of movement, while here these particles in the crystal, they just sit and wiggle around a little bit, while here they just move like crazy. And a liquid is literally in between, right? It has some sort of short range order a little bit, but it's intermediate density, a little bit of order, and a little bit of movement. Mind you, this is also what makes a liquid very difficult. Yeah, crystal is okay, gas is okay, but a liquid is in between, which makes it hard to look at. Now, if we translate this into the colloidal domain, then rather than looking at the temperature, we heat things up to melt a solid, we look at the concentration. That's our control parameter. So what do I mean by concentration? Concentration, I mean the number of particles in a given volume. Yeah? It's just basically how many balls do you have. And this is how you can illustrate this. Yeah? So this is now the colloidal phase behavior here. So you have a lot of particle in a given volume. These things will form what we would call a colloidal solid. This is the equivalent of a molecular solid, and it looks like this. If I now decrease the concentration, then I end up in a liquid. Yeah? So decreasing the concentration in the colloidal regime is the same as increasing the temperature in a molecular system, right? So concentration does the same thing as temperature, it just acts opposite. But that's the idea. And now to come back to Dirk's die-struct network and about colloidal liquid crystals. So these are just balls, right? And balls have a solid phase and have a liquid gas. Well, typically, strictly speaking, we call it a fluid, but it doesn't matter. They only show one thing. They go from a liquid to a solid. But if we now look at, say, rod-like colloidal particles, they have a liquid down here. But if you pack them, increase the concentration, so more and more of these, they go through these liquid crystalline phases, and Dirk has already shown a movie of this, pneumatic, smectic, and a solid phase at some point, and even the particles that are disc-like do the same thing. So I don't really want to go into too much detail, but we can study all these different phase transitions in colloidal systems as well, not by changing the temperature, but by increasing their concentration. Right? They go from a liquid to liquid crystals to solids, depending on the shape of these particles. And just to show you that's really true, I have a few examples here. So this is the schematic picture. This is a real picture of a colloidal crystal made with a microscope. And you can nicely see the regular pattern of these particles. And down here, if we decrease the concentration, we're in a liquid kind of state. And this is a particularly beautiful picture from Utrecht, where you see colloidal silica rods that Dirk has already mentioned. And they're nicely oriented, arranged themselves in these smectic layers, as we call them. This is a quite exotic phase behavior. But you can really do it with colloidal particles. And the nice thing is, of course, you can see it. These are all microscopy images. Okay, so the next thing, we're going back to Arran now, because I would like to show you this in a real example, right? What we're going to do is we're going to more or less start out here, and then we're going to slowly increase the concentration, and you will see it sort of crystallizing or forming a solid spontaneously. So, Arran, we're going to go for the... Yeah. So start at the liquid side. So this is what you can see, yeah? It's a really almost a gas here, and then we start going slowly towards the more concentrated side of the sample. You can see the particles nicely moving, and you can see it getting a liquid. It's a liquid. Just stop there for a minute. Yeah, you can see here is the density. The concentration is a bit lower. Here it's a bit more concentrated, but it's still no real ordering, right? It's not a regular pattern because the concentration is not high enough. In other words, the equivalent of the temperature is not low enough. So keep going a bit. Still no crystal. We have to wait for a bit. We have to wait. Can you go? Yeah, there we start seeing something. Stop there for a minute. So you can start seeing these rows appearing, these regular patterns appearing from these colloidal particles, which is really what a solid should look like at some point, right? And the only thing that we've done here, liquid-like, is a low concentration, and we keep increasing the concentration, and we just see the phase transitioning happening as we are speaking here, right? So you can just see it, and that's the power of studying colloidal systems. We can just look at it. Can you go a bit further, or then we hit the edge of the sample, or? Yeah, okay, we start seeing multi-layers, so stop here for a minute. So this is a beautiful hexagonal crystal here, and we just started in a liquid, right? And the only thing that we've done is actually increase the concentration. Mind you, this is a monolayer of particles, and we start seeing second layer particles here, so this is see some out of focus blurs, basically. The crystal is trying to go from a single layer crystal to a multi-layer crystal just because it can't pack more particles in the plane. And this is really a lot of particles, but we're struggling to show you the focus. But then we have another technique, which is another demonstration in a minute. But yeah, go back to the crystal a little bit. Yeah, beautiful. Here, a vacancy. Beautiful. Huh? So these are very, very typical defects you see in solids, but you know, we can see it, and we can, at some point, these things actually move around, because you can see this particle is trying to get away from it, and is trying to fill this gap. And that's what we study typically in the lab. Good, Arran. I think you're switching the objective now?
Yeah.
Okay, cool. I'll go on and do some microscopy then.
Okay.
Okay. So that's a bit about the introduction into why we study these systems. So what I'm going to talk to you now about in the last 20 minutes is I'm going to talk to you about the techniques that we use to study these systems. Of course, you've seen the techniques already in action because everything you've seen was microscopy, but I'm now going to say a few more words about this. And in particular, I'm going to talk a bit about optical bright field microscopy and confocal microscopy, and then at the end we'll do some optical tweezing. So microscopy is an old technique. Well, I don't know, depends what you compare it with, but it's still going very strong, right? Everything in our lab, every setup in our lab has a microscope objective and a camera. Basically, we do only microscopy. You can also use different techniques, but for now I want to focus on microscopy. So it's a bit disputed as to who was the first one kind of inventing the microscope, but there were certainly Dutch people involved. So Zacharias Janssen, Anthony van Leeuwenhoek, of course famous, and Robert Hooke, somebody from the UK, an Englishman, also played an important part in this. And let me just show you, talk to you a little bit about this, but only very briefly about these microscopes. So Zacharias Janssen made this thing, and this is believed to be a picture. This is the design, and this is called a compound microscope. And why it's called a compound microscope is not really important, but it has basically two lenses. There's one objective of one lens here, and there's another lens here, and that's what he used to look at his sample. Okay, so then Anthony van Leeuwenhoek made a slightly different one. This is what's called a simple microscope, and it only has a single lens, and it actually sits here, right here, this little hole. That's where the lens sits. Yeah, so you would look at things like this with a single lens. So a little bit later, we had Robert Hooke, who also made a compound microscope, and a compound microscope consists of two lenses, right? So this inside here, we would have also two lenses similar to that one. But the big improvement that Robert Hooke is that, for example, he was the first to make a microscope stage. Yeah? Looking at an image, making an image of a sample also comes down to actually fixing the sample. I mean, trying to make a photograph of something that moves is very hard. If you make a photograph of something that's still and fixed, it's a lot easier. You get a lot better pictures. Right? So while the optics was very similar to this tube with two lenses, Yeah, there's also 2 lenses in there. He had a whole stage around it and all sorts of things, which really make a big improvement of microscopy. And Robert Hooke, this was very nice. Dirk organizes a lot of nice conferences, but we had this Micrographia Day. So this famous book by Robert Hooke is Micrographia. And it's actually, was it the first print in Christchurch? Or, well, you have the book in any case. So we've seen, I've touched the book even. It's very, very cool. It has beautiful illustrations of all sorts of small animals in there. And he could do that because of this microscope and the stage. But you know, the microscope only had 2 lenses inside. So it's well worth visiting Oxford anyway, but if you have a chance to see that, it's really very nice. Okay, now I'm going to make a big jump because you know, this was 1635, so now we go to today. And well, the disappointment, I don't know if it's a disappointment, for me it's actually not that disappointing, but the microscopes today are not that different actually. Yeah? So our microscopes typically have 1, 2 lenses, exactly the same as Robert Hooke had. So we position them slightly differently. So the optics is a bit better, the lenses are a bit better, but the principal design of these things is not that much different. And I just want to emphasize 2 different techniques here. One is bright field microscopy, that's how it's called. And this is the most complicated diagram I'm going to talk about. So what we have is, we have a sample, which is this gray box. And we have these 2 lenses here. And as you know from making a photo, there's always a bit that's in focus, and behind them and in front of it, there's always blur, out of focus. And whatever is in focus sits inside this image plane here. There's this dotted line. And these red light rays, they're actually coming from the focal plane, the image plane. And if you then follow these beams through, you get a nicely focused onto your camera, which is your chip in your photo camera. But of course, all the light that originates from a point above or below the image plane also hits the camera. And this is really what the out of focus blur actually is. And that's what you just saw in the image when Arran saw a lot of particles sitting on top of each other. We couldn't get a good focus because we got a lot of out of focus blur. Yeah? But we can do another trick, is we can actually make something called a confocal microscope, which is exactly the same thing. The only thing that we are doing is actually placing a, whereas here we had a camera, we would actually place a pinhole at the focal point and then the camera a little bit behind it. Which means that whatever is originating from the image plane here, boom, 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 is nicely passing through the pinhole, and that's what you're going to see. But whatever is not originating from the image plane, i.e. a little bit above or below, will actually not get through the pinhole and doesn't actually blur your image. Yeah, this is a key thing, which means that everything that's out of focus, above or below, we just cut it out. And there's a little bit more to this, but that's essentially the idea. And we'll try and demonstrate this now. We're going to look at a sample where we first use bright field, and then Arran's going to put in a mirror, and we switch to confocal. And you will just see the image clearing up completely. But before we do that, we may have a small look at the microscope, and I'm just going to show you these 2 lenses, because then you've seen it. Okay, Arran, I'm going to switch to you.
Yeah. Got a live camera.
Okay, that's cool. So this is our microscope. I hope you can see it's a bit dark, but what you have here, this is our sample. Yeah, and on top of this is just a light bulb. We're just illuminating our sample. And here you have the first lens, which is just a microscope objective as everybody may have seen. That's basically acts as a first lens. And then there's a mirror down here, and the light comes out here. And this is my second lens here. Yeah, just like the Robert Hooke microscope. And then here we just have a filter, which doesn't matter. And then the camera, very big camera, is sitting here. It's this big. It's as big as my thumb, this camera. It's beautiful. The first time we tested it, it came in an envelope, and I thought, where's the camera? But yeah, it really was a camera. So this is the essential parts of a microscope, right? A sample, 1 lens, 2 lens, and a camera. That's it. And a light bulb up here. Good. Now, Arran, let's go to the sample, and this is basically a thick sample. So here we have a lot of colloidal particles, yeah, 3-dimensional sample, and we're trying to image this with bright field, so without a pinhole. And while some of this stuff is a little bit in focus, it's very blurry, and it's very hard to get a really good crisp image here. Yeah, so you try and focus something. There's always something in focus, but there's always a lot more out of focus, which you never get a good picture. So you go up, and the sample is very dilute. You can tell it's very dilute, but you can't actually really distinguish the particles. So maybe go to a concentrated bit, Arran. Yeah, good. And maybe we switch to confocal, if we can do this. So there we go. This is now confocal. So we just need to look for these things a little bit. Try and get it in focus, but you can clearly start seeing the particles much, much better than. So it's a bit dim. So Can we increase the gain a bit, or?
Whoa.
That's a lot.
Sorry.
So trying to switch it, this is always the challenging part, but
Is that so clear at your end?
yeah, it's a bit noisy. But the point is you can see the particles much better. Maybe try and find a fresh part of the sample. It's not quite as good as I hoped for. So
Yeah, sorry.
we can get, well, you know. I have some images, I'll show you that in a minute. I'll show you a few images and then... No, it's not going to be quite good enough, I think.
Okay.
What do you think? Just keep trying and then I'll ask you, if you get a good image, I'll show the image here anyway. Oh, on my screen it's already better. But yeah, it's always a good excuse, huh? On my screen it's already better. But, right. Good. Let me just show you here. So this is what a real 3D image could look like, right? So we can actually make these images at different heights, and you can really get a three-dimensional image of fluid, and you can clearly see all the particles separately very, very well. And you build up this three-dimensional image by making all these images at different heights and stitching them all together. But of course you cannot do this if every image is completely blurred. Let me see, because I have this this slide here as well. This is how a confocal image could look like, really. Right? So this is very, very clear, very, very good contrast, and that's what a pinhole can do. And then, you know, if you image this in 3 dimensions, you get this cube which I just showed. So I don't think we quite managed in the lab to get it that good, but you know, this is the idea of a pinhole. And these are the two main techniques that we use. And of course, you have a lot of other microscopy techniques, such as you know, phase contrast or DIC or electron microscopy works very differently. Dark field illumination, but these are for us the two mainstream ones: bright field microscopy, which you actually see an image of here, confocal microscopy. These are the two different things. Arran, did you find anything?
It might be a little bit better.
Okay, that's worth a go then. Let's just try. Ah, yeah, okay, well they move a lot. Well, the fact that they move is important, right? Because it means it's like photographing somebody that moves very quickly. It's always a bit blurry, not because it's out of focus, but just because it's moving. But you can still see the particles much better than you could see them in a bright field image. So yeah, I think this is what we're going to have to be satisfied with for today, because we want to finish before coffee. Good. Okay, Arran, shall we move on, and then next time I'm coming back to you, we'll do some optical trapping?
Yeah.
Okay, great. Nice crystal, huh, by the way. Good. Now the last part of the last 5 to 10 minutes of my talk, I'll actually move on to manipulating the microworld. Yeah? So we're going to manipulate these colloidal particles now, because up to now we've only passively looked at it. Yeah? We put the sample on, put them under the microscope, and just looked at them. It's also very useful if we can manipulate them, and that's what we're going to do now. This is something called optical tweezing. This is one way of doing it, but there are many ways of doing it, but I only have an hour. So we'll just stick to this. Now a key property of colloidal systems as to why you can actually manipulate them is that colloidal systems are soft. Right? So if you have a molecular solid, or say even an atomic solid, it's even harder, but it's usually very tough. Right? If you have a cube of ice and you just throw it on the floor, it's usually still a cube of ice. Yeah? It's not suddenly gone. Right? And if you want to sort of you know, have a big block of ice and you want to get a small piece off, you actually really have to take a hammer and you know, use a bit of force to actually break it. Now if you take our colloidal crystal here, say an opal, this breaks and scratches really easily, right? If you throw it on the floor, it's gone. Even with your finger, you can scratch it completely. And the only reason why you can do that is because these things are very, very soft. So there are deep reasons for why this is the case, but for this talk, it's just important that you realize that it's very easy to break a colloidal crystal. I have one in my lab, and if students pick it up and shake it, I'm very upset because it's gone. Yeah? If you have a cube of ice and you shake it, it's still there. And that's the big, big difference. So I always say very, very careful with these things. So if you ever buy, an opal, be careful with it. Now, to put this in numbers here, so if we want to deform colloids or colloidal particles or say a colloidal system, this is the amount of force that we need, right? The Newton is just a unit of force, and this is 0.0, and then a lot of zeros, 1. Yeah, this is a fraction of a piconewton, which is just a tiny, tiny force. And just to put it in comparison, if you want to lift me, you have to use about 800 newtons. I'm not trying to suggest anything about me, I'm just trying to illustrate how easy it is to deform a colloidal system. Yeah? And this, as I said, enables us to actively manipulate these colloids. We can use electric fields, we can use magnetic fields, we can use flow. But in this talk, I'm just going to show you how we can use light to do this. Yeah? Because light, you can manipulate colloids with light, because light carries momentum. And this is this, James Bond and Goldfinger, and he knows all about why light carries momentum, because, I don't know who's seen the movie, but it's not quite that bad, right? So if this idea about transferring momentum is, if I'm standing here and Dirk would just bump into me, I'll probably, not quite fall over, but I'll move. Which means that some of the momentum that he has, he transfers it to me, and I'm moving. Yeah, and the same thing happens when light hits me. It's just that I'm too heavy for light to actually make me fall over. But once you go to the colloidal domain, so I'm, almost 2 meters, 180, then nothing much happens. But when you go to a colloidal particle, which is 1,000,000 times smaller, then a little bit of light can actually do the trick. Yeah? With light, we can actually hit the ball, a little colloidal particle, and shoot it off. So this is just a matter of length scales. So it's a typical size is extremely important here. And the way this works is literally like this. So I borrowed this from our Kishan de Lac here in St Andrews, up in Scotland. And it's a beautiful picture of a focused beam of laser light. Yeah, so you just have a laser pen here, which is also laser light. It's just not focused. But if you put this in put a microscope, a lens here, you can actually make a nice focus of this, and the focal point sits somewhere in the middle. Now, while this is not doing much to me, if I put a colloidal particle in there, what the colloidal particle is going to do, because of the transfer of momentum, it's going to sit right in the middle of the focus of the laser beam. Yeah, and I'm not going to go into too much detail. This has everything to do with transferring momentum. And this is what we call optical tweezing, literally, like you hold something with a tweezer, something small. Yeah, optical tweezing, optical trapping is the same thing. So 2 different terms for the same thing. But the point now is, if I move this laser beam, the particle, of course, wants to stay in the focus, the particle moves with it. Which means I can grab a particle and drag it around, literally, with a laser beam. And you can imagine this as follows a little bit, like a very simple explanation. Is this particle in the laser beam behaves like a ball in a bowl. Yeah? So if you have a ball, put a ball in there, and you shake it a bit, the ball is not going to actually come out. It's going to be stuck in this ball, unless you really, are very violent. But anyway, this is the idea. And how you can depict this schematically, of course, that this, imagine, is the ball. This particle is actually just moving around, like this, in this ball, in this optical laser trap. But it's actually never really leaving the ball. This is kind of important. This is what I'm going to show you in a real experiment. So this is what optical trapping moves. So if I move the ball, I move this parabola here, that particle is going to wiggle, but it's nicely going to wiggle wherever the laser sits. And that's important. That's what optical tweezing is. In fact, with optical tweezing, you can measure. We will show you in a minute that we can actually really measure this parabola, because this is what you would call an optical potential energy well, right? So the particle is stuck in the well, and it can't get out. So we can measure this in an experiment now live. So we'll just, we'll do this. We'll first have a quick look at how an optical tweezer looks like actually in our lab, and then we'll show you the optical trapping of particles, and we'll show you the potential energy minimum, the optical well, basically the ball that the particle is stuck in. But in this time it's an optical ball. Anyway, Arran?
Hello.
Good. So that's our laser. Yeah, stop here. This is our laser. There's a fiber-coupled laser beam coming in there. It's an infrared laser beam, and it's very powerful. As you can burn a hole in a piece of plastic with this without much problem. So once I had a PhD student who wanted to measure where the beam was. And I said, okay, well, you have a viewing card, you can use that. And he said, well, I have something else. And he just burned a hole in a piece of plastic and said, that's where the beam is. But anyway, so typically we don't really do that. But anyway, so the laser goes in here, and I'll talk a little bit more about this thing. This is a very special mirror, and actually, in view of this conference, it's a liquid crystal mirror. It's a phone display, nothing else. So the laser is bounced off here, and then it's going to hit this mirror, and then, can you go a bit towards the objective? Yep, so the laser is traveling through, one lens, two lens, and here is the objective again, and then the laser is going up through this objective into the sample, and we achieve our optical trap, more or less, because the objective focuses the laser beam down. Good, so Arran, maybe we can, so you can see the objective clearly here? Yeah, okay, there's another light bulb here, but the sample sits here. This is the objective. Perfect. Thanks, Arran. Good communication. Good, so maybe we can have a look at some colloids being trapped. So now there's laser light coming through. You're not going to see any of these beautiful things because it's infrared, right? Our eye can't see it, which makes it even more dangerous, but that's fine. So you can see some colloids moving around. So you have one which is trapped. I guess it's this one. So now we're going to move the whole samples, but everything is moving but one. So can you move the trapped one around, or? Ah, there you go. This is not the colloid doing, this is the laser beam doing it. Oh, we trapped another one. There's always two ghost spots. Yeah, so these ones are freely floating around, diffusing. This one is actually sitting in an optical laser. So we actually move a laser beam and traps the particle, and we literally, Arran is now with his mouse dragging this particle around. Which means that we can measure these tiny, tiny forces. We can really measure these things. So let's try and measure this parabola. So that's going to show down here. Because if we image a particle that's trapped for long enough, it's going to do this rattling motion. And thereby scanning this parabola, it's going to explore the bowl, the optical bowl around it. And you can just see, now it looks like nonsense. But if we just wait a few minutes, you see the particle, the trajectory is going nowhere. It's wiggling, but it's not going anywhere. And now we start to see this parabola already. So if we wait a bit longer, this is going to be a very nice parabola shape, which really shows the optical bowl that this particle sits in. It's very, very similar to a particle sitting in that bowl, and it can't get out. Yeah, you see, particle just moves, doesn't travel off, and wow, beautiful. Yeah, so this is basically an optical potential, literally the optical potential energy. So we can really calibrate this thing, and it acts like a spring, and we use it as a very sensitive tool to measure tiny, tiny forces in colloidal systems. And the key experiment to do is really this, where you know this potential energy landscape. But yeah, it's nice, and nowadays all this is automated, and we can do this in the lab. And once we know this, we can do a lot of other experiments. And it starts the risky thing here is that it gets more beautiful the longer you wait, because you get more statistics. Basically, it's just building up statistics. But in the view of the time, I'm going to leave you with this beautiful parabola, but really a live one now. Which is kind of a nice experience. Good. Arran, I'm going to move on to do some spatial light modulator stuff. We'll come, don't go offline. We'll just come back to you, but we'll just move on. Okay, good. So the last couple of slides is really about 2 minutes left now, is I'm just going to show you some advanced stuff. So this was just a single particle in a single optical trap being moved around, and that's already very powerful, but we can do better than that. And that is, we can use this liquid crystal mirror. This is a nice little bridge into the liquid crystal talk as well. So this mirror, you've seen it, we call it a spatial light modulator. Now you can forget this again. It's basically a liquid crystal mirror. Yeah, so what you can do with this, you can shine one laser beam onto it, and then by displaying something fancy onto this thing, you can actually get 4 laser beams out, or 5, or any sort of laser beam. You can really manipulate this thing. And what this liquid crystal mirror is nothing else than a phone, more or less. Yeah, so this is Arran's phone, new iPhone. He's very proud of it. And if we display, so this is what is called a hologram. If you display this hologram onto his phone, or onto this piece of onto this liquid crystal mirror, then if you shine a laser beam on here, what comes out is exactly 4 laser beams. And if we change this hologram now dynamically, all the time, that means we can move these 4 laser beams around. We just update the hologram all the time. Are you just playing a movie on your phone, shine a laser beam on it, and you get all sorts of difficult, complex patterns out of it. Yeah, we can make 4 traps, and we can also make 8 traps. We can make traps rotating, and some of you have seen these movies already, but it's worth seeing them again, I think. You know, we can trap 8 particles. I made this joke already. I don't know, Arran drew 4 and has 8 here, but, you know. Yeah. So yeah, that's better than 1. And to finish this whole thing off, I'm just going to show you a few examples of complex and dynamic optical tweezing patterns, what we can achieve in the lab. And these are just not there to understand, it's just to really there to enjoy watching. So what this is bright field microscopy, and we have 4 particles in an optical trap. What we're going to do now is they're all in optical trap. We're going to form a tetrahedra from them, and then rotate them around, yeah, in 3-dimensional space with optical traps, and then they will come back into the plane to form this cube. Yeah, so it's amazing videos. So there you go. All laser guided. You see them going out of focus because it's bright field. And we rotate them nicely around the whole tetrahedra, and now they're going to come back into the plane, back where they started. And you can do this with sort of really fancy spatial light modulator. You can really, oh yeah, that's another one, which I should show. With light, you can also exert angular momentum. So rather than just pushing a particle, you can also make it rotate if you do something very special on your iPhone or your mirror. And then this thing, oh, well, it's nice seeing it again. But this is going to rotate. You already saw it rotating. It's very cool. So here you can see we have all these particles trapped. We can just make these things spin around like a tumble dryer, more or less. Here we do the same thing. So this is confocal microscopy. We trap this one here, and we make it go around in circles while we are imaging the colloidal crystal around it. Right? So this is a very powerful combination of imaging a thing. And here we do something more fancy, where we're actually going to rotate this whole block here in one go. And then you see a fault line here, right? You see a bit of where the crystal, so if you look at this, the crystal here, it has this direction and then changes the direction, and this is this fault line, and we can really manipulate this using all these optical trapping, and we can learn a lot about these sort of interfaces or the elastic properties of crystals, and that's how we use the combination of optical manipulation and imaging. Good. So this brings me to the summary of my talk. I have 20 seconds left, so that's perfect. I hope I've shown you in the past 45 minutes that, you know, why we study colloidal particles, because they're found in numerous situations, both in natural systems like blood, but also in many industrial applications like paint. And, you know, that's a reason alone to study these things. But also, we use them a lot as a fundamental model system to study the behavior of atomic systems, the phase behavior, and understand these things. And the advantage, of course, is that, you know, as I've shown you, we can simply image them. They're just big enough to use a simple microscope, be it bright field, be it confocal, to see them, to follow them, and see on a single particle scale what's actually happening. I mean, you've seen it yourself, how something goes from a liquid to a solid, but that's one of the big advantages. And finally, what Dirk and I use a lot in our lab is the actual manipulation. And in this case, I've shown you the example of optical trapping. Arran, what's happening? Not part of the plan. So, we can manipulate, deform, and do all these things. So I wanted to go back to Arran just to thank him for everything, but yeah, we'll see. Arran, are you still there? Okay, good. So this is...
I think the lab burnt down.
Yeah, I think I'm going to go back to Oxford now. I'm done. To see what's going on now. Anyway, so let's... so Arran, are you there? Something has started going very noisy. Anyway, I just wanted to say I'm done here. I'd like to thank Arran for your help getting all this done. Can you hear me? Yeah. Anyway, it's all allowed to break down now. So let's thank Arran, and I'd like to thank you for your attention. And he's just gone offline, so let's keep it at that. He's calling me. I'm done, people. Thank you very much. Thank
you very much, Roel. That's absolutely excellent. Are there any questions? Andy?
How did you reach liquid like order and solid like order at the same time with the same
set sample.
Very good points. What we did with this sample, that all the particles are lying on the bottom, we put it on a slight tilt, and we left it there for a good few days, so that at the bottom of the cell there's a lot of particles, and at the top of the cell there are not so many particles, and somewhere in the middle this phase transition from a liquid to a solid is actually happening.
So it's just a demonstration?
Exactly that. It's basically Curran's experiment. Yeah.
Are there any other urgent questions?
Aaron, you're online, huh?
Yeah. If not, I think we should thank Roel, but also especially Arran again. And we have to clap very loudly so that you can hear it. Thank you very much. We'll be coffee and we should be back at around 10:30.